Good morning, everybody.
Good morning.
Okay. How is everyone doing today? How is everyone today?
Good.
Can you guys hear me?
Yes.
Okay, it's okay to speak, okay? Anyways, so if you don't want to speak there, I'm going to begin here. So today we are going to continue with the chapter probability that we have started in previous class. Today we'll be looking at a couple of rules on probability. The first one is going to be the addition rule for probability. So in addition rule, there are two types here. I break this addition rule into two parts, but you'll be using the addition rule when you see the word or in the problem. If you see the word or in the problem, then you'll be using the addition rule for probability. So what happened here is, in the first part, if there are two events A and B, as I have shown here in this diagram, and there is nothing common between those two events, then we say that the events are mutually exclusive. That is, there is nothing common in between those two, or the events are disjoint. So if the events are mutually exclusive or disjoint, then the probability of occurring the events together is not possible. Okay, so in that case, we say that the events are mutually exclusive, and for mutually exclusive events, the probability of A or B is equal to the probability of first event plus the probability of second event. So highlight that formula. So this is the probability for the mutually exclusive events or disjoint events. And in the question, you'll see the critical word or. So let's take an example. Here is the example. A bag contains 16 white marbles. So let's see what is there. A bag contains 16 white marbles, 3 red marbles, 9 blue marbles, and 7 yellow marbles. So you can see inside a bag, you have 4 different types of marbles: 16 white, 3 red, 9 blue, and 7 yellow. That means if I want to find the total number of marbles, total will be 16 plus 3 plus 9 plus 7. So if we add all these, the total number of marbles will be 35. Total number of marbles in the bag is 35. Now in part A, if you look here in part A, what we are asked to do is, we have to, if a ball is, or if a marble is drawn at random from the bag, you have to find the probability that it is a yellow or white marble. So there is the keyword or there. So we are looking for probability that the marble is yellow or white. We are looking for the probability that the marble is yellow or white. So you know that a yellow marble cannot be white and white cannot be yellow. That means there is nothing in common. Okay, so meaning of that is this has or, so it is addition rule, and there is nothing common between those two events. So this is mutually exclusive events. So if we are calculating the probability of mutually exclusive event, we have seen in the previous slide, it is the probability of the first event plus the probability of the second event. So that is probability of occurring or probability of getting a yellow marble plus the probability of getting white marble. So here, probability of getting yellow marble, we have yellow 7 out of 35. So it will be 7 over 35. Plus the white marbles, you can see we have 16 out of 35. So 16 out of 35. And if we add these two, 7 over 35 plus 16 over 35, you have a same denominator. So you can add the numerator. 16 plus 7 is 23. So it will be 23 over 35. And if we simplify this to change it to decimal using calculator, it should be 0. Make sure you check it. 0.5429. So that is the probability of occurring a yellow marble or white marble. Is there any question on this one? Just say yes or no.
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 No question on that. Awesome. Now let's look at part B, a very similar question. In part B, we are looking for the same question. If a marble is drawn at random from the bag, we have to find the probability that a red, blue, or yellow marble occurs. So you can see there is the word or there. So we are looking for probability that the marble is red, blue, or yellow. So if there is or, we are using the addition rule. And now if you look at, if you try to check whether there is anything common or not, whether the events are joint or disjoint, okay? A red marble cannot be blue or yellow. Blue cannot be red or yellow cannot be red or blue. That means there is nothing common between them. These are disjoint events. So if the events are disjoint, what we do is, this is the addition rule. So we find the probability of first plus second plus the third, just the extension of the rule here. So probability that the marble is red plus probability that it's blue plus probability that it is yellow marble. Now we can write the probability of each. Probability that it will be red is 3 out of 35. So 3 out of 35. Probability that it will be a blue marble. Blue, we have 9 out of 35. 9 out of 35. And then the yellow marble, you can see we have 7 of them. So 7 out of 35. So we have a common denominator of 35. If you add the numerators there, 3 plus 9 plus 7 is 19. So the probability is 19 over 35. And if we simplify this using calculator, you must get 0. Make sure you check it. 0. Okay, hold on. The previous probability, I don't know whether you checked that or not. 23 over 35 is 0. It should be 0.65. 0.6571. Make sure you check it using calculator. Similarly, this one will be 0.5429. 5429. Okay, one more time. Please check this. 23 divided by 35. The first answer should be 0.6571. The second one is 19 over 35. That's what we get here. So it is 0.5429. So in this example, what we have done is we have the question with the word, critical word or keyword or. That means we have to use the addition rule. And when you look at the events, they don't share anything common. That's why these events are mutually exclusive or disjoint. That's why we add the individual probabilities to find the probability of the events given in the problem. So this is the first part of the addition rule, and it is called the addition rule for mutually exclusive or disjoint events. Are there any questions on first example? Just say yes or no. No question?
No.
Okay, great. Great. Now we are going to move on to the second part of this addition rule. It's called the addition rule again, but this time this is the addition rule for non-mutually exclusive or sometimes called inclusive events or joint events. Okay. Here also the key word that you'll see in the problem is The key word that you will see in the problem is or. And for the non-mutually exclusive, the other word for non-mutually exclusive is inclusive. So here we are looking for the probability of inclusive or joint event. That means when you're looking at two different events, there will be something common between those two. So like in this picture, you can see this first circle and the second circle, if they are events A and B, if they represent event A and B, then there is something common in those two events here. Okay, there is something common between those two events. So in that case, if we want to find the probability of A or B, then what we do is, like in mutually exclusive, it will be probability of A plus probability of B, but we subtract the probability of the shared reason. Okay, we subtract the probability of this shared reason. So minus the probability of A and B. So if two events, one more time, if two events are inclusive, that means they shared something in common, or if they are joint events, then the formula will be probability of A or B is equal to probability of A plus probability of B minus probability of A and B. So that is the formula. Let's take an example so that this will be a little more clear. Here is the example. So again, this is based on the cards. So I'm not going to go over these cards again because we did that in previous class. So you have the idea of the cards. We're directly going to solve the problem here. A card is drawn at random from a well-shuffled deck of cards. When we say well-shuffled deck of cards, we have 52 cards there. We have to find the probability that, okay, in the first part, probability that it is either an 8 or a diamond. Okay, so we are looking for probability that it is an 8 or diamond. Okay, so when you look here, we are looking for the probability of getting an 8 or a diamond. There is or, so this is the addition rule. But now we have to see where there is anything common between these two. Now, when we look at this, can we have an 8, which is also a diamond? The answer is yes, because if you look at this card here, this card is an 8 and also it is diamond. And here, the other way of looking at it is, can a diamond be 8? Yes, a diamond can be an 8 also. See, a diamond has 8 there. That means there is one card, that is shared between these two. 8 can be of diamond, or diamond contains 8. That means they have something in common. That is, this is the mutually inclusive event. So we use the proper formula here. It is the probability of getting an 8 plus probability of getting diamond. Now we subtract the common minus probability that it is an 8. It is an 8 and also it is diamond. The reason is this is the mutually inclusive case, joint case. So if it is a joint case, this is exactly what you should be doing. Now, once you have this formula set up, now what you have to do is you have to plug in the values. The first one is probability of getting an 8. If you look at 8, there are 8, we have 4 of them. There are 4 8s out of 52. So that'll be 4 over 52 plus probability of getting diamond. You can see diamond, they are here. You have 13 of them, 13 diamond out of 52 minus the cards. They are both 8 and diamond. We have only one of them here. So it is 1 out of 52. So now you have a common denominator of 52. In the numerator, you have 1 plus 13 minus 1, which is 16 out of 52. So that becomes 16 out of 52. And if you simplify that using calculator, you should get 0. Make sure you check this. 3077, 0.3077. So that is the probability of getting an 8 or a diamond. One more time, when you're looking at this probability, they share these two events, getting probability of getting an 8 and probability of getting diamond. They share something in common. That is, there is one card that is the diamond or 8 of the diamond that's common to both. So that's why this is inclusive event, and we use that formula. Before I move on to part B, is the first part clear to everyone in the class?
Yes.
That's good. That is good. Okay, now let's look at part B. So in part B, the question is the same question. Find the probability that it is either a red card or a king. So probability of getting red or king. Because there is or, we are going to use addition rule, no doubt on that. If we are looking at a problem with or, it's addition rule. Now we have to see whether there is anything in common or not. Okay. A red card, see, if a card is red, does it contain king? The answer is yes, because there are 2 red kings. And also, if it is a king, can it be red? Yes, there are 2 cards like that. So that means they share something in common. So that means here also we have to use the formula for mutually inclusive or the joint events. So the formula will be the probability of red plus probability of king, then minus probability that it is red and also it is king. Now, if you try this, probability that it is red, there are 26 red cards out of 52. So 26 over 52 plus probability that it's king. There are 4 kings out of 52. Then minus probability that it is a red and also king. Red and also king, there are 2 cards. That is the king of heart and king of diamond. Okay, so 2 out of 52. So if we simplify this, so we get the probability of red or king will be equal to, okay, if we simplify this, we have a common denominator of 52, 26 plus 4, 30, minus 2 is 28 out of 52. 28 out of 52. And if we simplify this using calculator, make sure you try this. What I get here is 0.5385. 5385. So probability that the card is a red or a king is 0.5385. So this is how we can solve the problem involving the word or, that is the addition rule problem. Okay, and we look at 2 different types of events here. One is the disjoint or mutually exclusive, and the other one is mutually inclusive or the joint event. So before I move on, do you guys have any question, or are there any question on this example? Is this example clear?
Yes.
Yes.
Good. Okay, now let's look at a summary of what we have done so far. Hold on, what's going on? Is my internet a little slow? Am I breaking a bit, or what is it going on there?
No.
No, it's coming clear. Okay.
Yeah.
Let me try to share my screen again because it is not letting me share here. So I'm going to try again. Sometimes technology is a problem. So let's see. Okay, I hope it will let me share. Okay, there we go. It's back there again. Can you see my screen?
Yes.
Okay, so this is the summary of what we have done so far. If 2 events are non-mutually exclusive, that means inclusive, we have to subtract this part that you'll see here. But if it is mutually exclusive, it is just the sum of the probabilities of 2. That means if the events are mutually exclusive, this part of the formula is 0. So we can also say that if two events are mutually exclusive, the probability of the shared part will be 0. So we can say probability of A and B is equal to 0 for mutually exclusive events. So please highlight that last sentence from this slide in your note catcher. Now let's try to look at two different or three different events and check whether they are joint or disjoint or mutually exclusive or not. Here is that example. See, they have given a sample space. Sample space is the set of all possible outcomes. They are like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Event A is 1, 2, 3, 4, 5. Event B is 4, 5, 6, 7, 8. So if we look at event A and B, you can see 4 and 5 is common. In event A and B, 4 and 5 are common. Similarly, if you look at B and C, in B and C, this one, 7 is common. In B, you have 7. In C, you have 7. Okay. And between A and C, there is nothing common. So if I want to represent this using Venn diagram, this is what I can do. A and B have something in common. So you can draw event A here and then event B here like this. Between event A and B, the common elements are 4 and 5. So that will go to this common region, 4 and 5. The remaining are in A, the remaining are 1, 2, 3. So we put it here, 1, 2, 3. Similarly, if we look at B and C, the common element is 7. So if I draw C here, the common element is 7. Now in B, if you look at B, we have 4, 5, 6, 7, 8. 4, 5, 7 is already there. So here in the middle, there should be 6 and 8. And then in C, we have 7 and 9. 7 is here, so 9 should be here. And if we represent the whole thing using a Venn diagram, this is your sample space. And you can see in your sample space, you have the elements from 1 through 10. So check here, 1, 2, 3, 4, 5, 6, 7, 8, 9. 10 is not here in these three circles. That means 10 should be outside these circles. 10 should be outside these circles. So what we have done is we represented the information using Venn diagram. Now we have to answer the question based on this one. The first part is, are event A and B mutually exclusive? Okay, mutually exclusive means they are disjoint. Are they disjoint? That is the question. So when you look at this diagram, what do you think? Is this A and B mutually exclusive or mutually inclusive? Do they include something in common?
Yes.
They are mutually inclusive,
Yes.
right? So the question is, are they mutually exclusive? The answer is no. Are they mutually exclusive? No. They are mutually inclusive instead. They are mutually inclusive. They are not mutually exclusive. Instead, they are mutually inclusive. How about A and C? A and C, do they share anything in common?
Yes.
Yes.
A and C. Is there anything
No.
common
No.
between A and C?
No.
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 That means they are mutually exclusive, right?
Yes.
So they are mutually exclusive. They are mutually exclusive. So all you have to do is you have to look at the diagram and say, if there is something in common, then they are mutually inclusive. Okay. If there is nothing in common, then they are mutually exclusive. So A and C are mutually exclusive, but A and B are mutually inclusive. So that is the difference between mutually inclusive and mutually exclusive. So with this, we completed the first rule for today, that is the addition rule of probability. Before I move on to the multiplication rule of probability, are there any questions on addition rule of probability?
Yes.
What is
I
your
have
question?
I have a question. In
On
the
this one?
diagram,
Uh-huh.
you use 10, but it's not given.
10 is given here in S. See, in the sample space, you have a 10. It is not there in A. It is not there in B. It is not there in C. Meaning of that is, it is just in this big set called S here.
Okay,
Because
thank
S
you.
contains 10. That's why we label that as, 10 inside S, but outside those three sets A, B, and C. Does that make sense?
Yes, thank you.
You are welcome. Okay, now let's move on to multiplication rule. Here also I break the rule into two parts. Okay, so multiplication rule can be used to find the probability of two or more events that occur in sequence. So here the idea in multiplication rule is the events should occur one after another. Okay, the events should occur one after another. And the key word in the multiplication rule is and. If you see the word and, then we use the multiplication rule. And also in multiplication rule, one more time, events occur in sequence, one after another. But when the events are occurring one after another, suppose first event has occurred, and when the second event occurred, and the occurrence of the second event is not affected by the first one, in that case, we say that the events are independent. Okay, if the occurrence of the second event is not affected by the first one or does not depend on the first one, we say that the events are independent. In that case, the formula for the probability will be probability of A and B. So and means multiplication rule. That will be equal to probability of A times probability of B. Here we are saying that the probability of occurrence of B does not depend on the probability that A has already occurred. So when I just say this, it doesn't make a lot of sense. One more time, we have to look at the example and try to understand this. So just highlight that formula for independent events and we'll take an example. Here is the example, quite similar to what we have done before in addition rule. A bag consists of 8 red marbles, 7 blue marbles, 6 green marbles, and 4 yellow marbles. What is the probability of selecting a blue marble on the first try and then a green marble on the second try with replacement? So before we begin, how many marbles are there in the bag? Tell me, what is the total number of marbles?
25.
Okay, 25. That is right. So total marbles is 8 plus 7 plus 6 plus 4. That is equal to 25 marbles. Now the question is, what is the probability? So we are looking for probability of selecting a blue marble on the first try, blue. So you put the hand on the inside the bag and you pull it, okay? And you're looking at it. What is the probability that you'll get a blue marble? And what you're doing there after that is you are replacing it. You are putting that marble back in the bag, shake the bag a little bit, and then you try to pull the second one. So the first one is a blue marble and the second is the green marble. So probability of getting blue and green. So now if you think of this probability, when you pull the first marble blue, the probability of getting that marble is, you can see your blue marble 7 out of 25. Okay, 7 out of 25. Now you are putting that marble back in because you are doing it with replacement. So that means when you shake it well again, and when you try to pull the second marble green, the probability of getting that green has not changed or is not affected by the first drawing by pulling the first one. That means these are independent cases. So what we do is the formula will be probability of blue and means multiplication times probability of green. We are using this formula because the events are independent. Independent events. That's why we are using that formula. So now if you plug in the values, probability of getting a blue marble, you have blue 7 out of 25. Multiply to probability of getting green. If you look at green, you have 6 out of 25. Now, in order to multiply this, we multiply numerator with numerator, denominator with denominator. 7 times 6 is 42. Divided by 25 times 25 is 625. 625. So now if you simplify this using calculator, it will be 0.42 divided by 625, 0672. 0672. Make sure you check it on your calculator also. It should be 0.0672. So here in this example, the probability of getting this second marble green is not affected by pulling the first marble because we are replacing it back. And you can see that the events are occurring in sequence. First, you pull the blue one, you put it back, and then you are pulling the green one. So the events are occurring in sequence. So if the events are occurring in sequence and we are looking for the probability of one event and the second, the keyword and there, we use the multiplication rule. Is this example clear to everybody in the class?
Yes.
That is awesome. Okay, now we are going to look at the second part of this rule, and this is for the dependent case. So multiplication rule for the probability of dependent events. One more time, for the multiplication rule, the keyword is and. Okay, and when we say dependent events, when first event has already occurred, and when you try to perform the second event, if the probability of getting the second event depends on the first, then it is called the dependent event. So when the outcome or occurrence of the first event affects the outcome or the occurrence of the second event, then we say that the events are dependent events. And for dependent events, that is the formula here for the probability. Probability of A and B is equal to probability of A times probability of B given A. The vertical line that is there is given. So probability of A and B is equal to probability of A times probability of B given A. So it is very similar to the previous formula. In the previous formula, we used to have probability of A times probability of B, but here the probability of B depends on A. That's why B given A. That's how we have to write down. So that is the formula. Let's take an example so that this formula will be more clear to you. Now, as we come across so many examples, I hope that you have clear idea about the cards. So I have not spread all the cards on the board. Okay. Instead, I've collected them here because you know what is here in this standard card, standard deck of cards. Okay. Two cards are selected. Two cards are selected without replacing the first card. See, without replacing the first card. So that means you pull the first card, you hold it on your hand, and then pull the second, and then look at it. So the events are occurring in sequence, but what you're doing here is you are pulling the first card. So when you pull the first card, the probability will be 1 out of 52 because there are 52 cards there. So it will be 1 out of 52. But the second time, when you pull the card, the total cards remaining will be 51. So when you pull the second time, the probability will change because it will not be over 52. It will be over 51. That means the second events depend on the first. So this is going to be the dependent case. So here 2 cards are selected without replacing from a standard deck of 52 cards. We have to find the probability of selecting a queen and then jack. Okay, let me write this down. Probability of selecting queen and then jack. So because they depend on one another, the way we write the formula will be like this. Probability of Q, the first event, N means multiplication, times probability of getting jack when queen has already occurred, or given that the queen has already occurred. We write the formula like this because this is the case of dependent events. Dependent events. So if you can figure out whether the events are independent or dependent, then it is quite easy to figure out the probability. Okay, so here, this is the dependent case. So now, how do we plug in the values? Probability of getting queen. On a standard deck of card, there are 4 queens. So it will be 4 out of 52 because there are 52 cards there. 4 out of 52. And what you pull is a queen. Okay, we assume that the first card we get is a queen because it is the probability of queen. Now you are not putting it back. That means the total card is no more 52. It is 51. Total cards is 51. And one card that you pulled is a queen. Okay, the card you first pulled is a queen. Now the second one is we are looking for the probability of jack. You pulled queen, so 4 jacks are still there. Okay, 4 jacks are still there out of 51. So the probability of jack will be 4 out of 51. See, the second probability depends on the first because the total number has changed. For the first one, the probability was 4 out of 52, but for the second, it is 4 out of 51. So that is why these 2 events, they are dependent events. So now, what we see here is 4 out of 52, 4 out of 51. When we multiply this, 4 times 4 will be 16 out of 52 multiplied to 51. You can do that in calculator if you want. It will be 2652, 2652 or 2652. And then when you simplify this using calculator, 16 divided by 2652 should be 0.0060. If I write up to 4 decimal places, 0.0060. So this is the example based on the dependent events. So events should occur in sequence. The keyword should be "and" in the problem. So in that case, you'll use the multiplication rule for probability. Now, one thing to note here, if the events are dependent, you can see if the events are dependent, the second probability will be probability of the first given, probability of second given the first. But if it is independent, it is just the probability of the first and second. We just multiply. Okay, for the independent case, if you multiply and if they are equal, then that is the independent case. Before we move on, is the example based on that cards clear?
Yes.
Okay, that is good. One more time. I am running into this issue again. Let me share back again. Okay, it will take few seconds to load. Okay, there we go. So we did this. After this, so we have seen if the events are independent, probability of first and second is equal to probability of first multiplied to second. So if two events are independent, then the probability of A and B is simply probability of A times probability of B. So this one is the summary of what we have done so far. And one key here, if two events A and B are independent, then probability of A and B is probability of A times probability of B. So you need to highlight that last sentence there. That's very important. Now, based on that, let's look at example here. So here they have given in the first part, probability of A is 0.4, probability of B is 0.8, probability of A and B is 0.36. Are they independent? If they are independent, then you know that probability of A times probability of B is equal to probability of A and B. Because for independent, let me write that here. For independent events, what we have seen is probability of A and B must be equal to probability of A times probability of B. The values must be equal. If you find this product, it should be equal to probability of A and B. So if you look at the first one, let's try to find probability of A times probability of B. Probability of A times probability of B. Probability of A is given here, 0.40. And probability of B is also given. Probability of B is 0.80. And if we multiply, this is 0.32. See, probability of A times probability of B, probability of A times probability of B, if it is equal to probability of A and B, probability of A and B is 0.36. Are they equal? Look at that. Are they equal or they are not equal?
Not equal.
They are not equal. So are they independent? If they are equal, they will be independent. So no, yes, you're right. So they are not independent. They are not independent. They are not independent. Okay, similar question is here. Suppose a balanced six-sided die is about to be rolled and we define the following events. So event A is getting 1 and 2 on the face of the dice. B is 2, 3, 4, 5, 6. And we have to find whether A and B are independent or not. So first, what is probability of A times B? Let's find that. Probability of A times probability of B. If we look at probability of A, in A, we are getting only 2 elements out of 6 possibilities. Okay, 2 elements out of 6 possibilities. Multiply 2. Probability of B, in B, we are getting 1, 2, 3, 4, 5 out of 6 possibilities. So that means probability of A times B will be, if we multiply this, 2 times 5 is 10 out of 6 times 6 is 36. So that is the probability of A times B, probability of A times probability of B. So we get this one. Now let's find probability of A and B. Probability of A and B. A and B means something common. So what is common between A and B? If we look here, 2 is common. There is 2 in A and 2 in B. So the common and means something that is in between both of them, A and B. Common element is 2. That's only 1 out of 6. So now you can see when you find probability of A and B, you get 10 over 36. When you find probability of A and B, A times B is 10 over 36. A and B is 1 over 6. Are these two values equal? 10 over 36 and 1 over 6. Are they equal?
No.
They are not equal. So are these two events independent?
No.
They are not independent. Very good. They are not independent. They are not independent. So that is about the multiplication rule, the dependent and independent case. So that is the second formula for the day. Now we are going to move on to the third and the last one. That is the conditional probability. So conditional probability is, this one is the third rule. And the key word here is given. If you see the word given or given that, given or given that, then we use the conditional rule for probability. Okay, if we see the word given or given that in the problem, then we use the conditional probability. That is, if the occurrence of certain events depend on the first, in that case, we'll be talking about the conditional probability. For example, here is my formula. See, this is how we write probability of A, this vertical line is given B. Probability of A given B. Conditional probability, because there is given. Probability of A given B is equal to, always remember, in conditional probability, the formula is in the form of a fraction. In the numerator, it will be the probability of this first one and the second. Probability of the first one and the second. So here, probability of A and B. Divided by, in the denominator, it will just be the probability of this second, probability of B. So that is the formula. Make sure you highlight that formula in your note catcher. Probability of A given B is equal to, it will be the probability of the first and the second, so A and the B, and you divide by the probability of the second, that is probability of B. Okay, let's take an example so that this crazy thing will be clear. Okay, here we have a question based on the conditional probability. There are 100 birds in a zoo. 50 birds are male with brown eyes and 20 birds are female with brown eyes. 20 of the birds are male with blue eyes and 10 are female with blue eyes. Okay, so a lot of information about the birds. We are asked to construct a contingency table. That means we have to represent the information using a table. So here, if you read through properly, there are two things. We are talking about the color of the eyes of the birds, blue or brown. And we are also talking about the gender of the birds, male and female. So what we are going to do is, when we construct the table like this, we are going to represent those two things. So blue-eyed birds, blue, and brown-eyed bird, that's right, BR for brown. And then the male birds and female birds. So we make table like this and then put the information by reading the problem in the proper box. So here, if we read through the problem properly, see, 50 birds, these 50 birds are male with brown eyes. Male with brown eyes, 50. So they are here. 20 birds are female with brown eyes. Female with brown eyes, they will go here, 50. So 20, 20. 20 are female with brown eyes. Next, 20 of the birds are male with blue eyes. Male with blue eyes, 20. So they will go here. And finally, 10 are female with blue eyes. Female with blue eyes, 10. This is how we represent the data in the form of a table. And this table is called the contingency table. Okay, this table is called the contingency table. You must be able to read the table properly and then use the table to answer the question. In mastery exercise, there are several questions where the table is already given, but you must know how to read the table properly and use that to answer the question. In contingency table, if the total is not given, you have to first find the total. So what I mean by that, let's see. Let's do this total. We do the total of the rows and total of the column. We do the both. So total here. Now, if I add these two, 20 plus 50, that will be 70. So you can see that 70 birds are male birds. That is the meaning of that. 20 plus 10 here, that is 30. So 30 birds are female. Okay, so total will also give you some additional information. Similarly, if I add this column, 20 plus 10, 30. 30 birds are blue-eyed. And then here, 50 plus 20 is 70. 70 birds are brown-eyed. So this is the complete contingency table. So in the mastery exercise, if the contingency table is given without total, make sure you find the total. Okay, you find the total by yourself. So here, if you add 70 plus 30, that is 100, or 30 plus 70, that's 100. That is the total number of birds in the zoo. 100 is the total number of birds in the zoo. It's already given. So before I answer these two questions here, do you have any question on this contingency table?
No.
Okay. So if you have no question on contingency table, let's answer the question now, which is here. So the question is, if a bird is selected at random, what is the probability that the bird is, okay, we are looking for the probability that the bird is a female, female denoted by F in our table, given that, see, there is that keyword, given that means we write like that, a slash type of line, given that it has brown eyes, brown. That's how we write it. Probability that it's female, given that it's brown. So whenever there is given that, it is the conditional probability. And when you write the formula for conditional probability, you'll get a fraction. In the numerator, it will be the probability of the first and the second. So it will be probability that it is a female and brown-eyed divided by the probability of the second, that is probability that it is the brown-eyed bird. So that is the formula. Now, see, we are looking for probability that the bird is a female and also has brown eyes. So if you look at the table, these birds, these 20 birds, they are female and also have brown eyes. 20 out of 100. Okay, 20 out of 100. And the probability that the bird is brown-eyed. See, these 70 birds are brown-eyed. 70 birds are brown-eyed. So it is 70 out of 100. Now to simplify this, you have 100 in the numerator and also in the denominator. So those two will get cancelled. So it will be 20 over 70. And 20 over 70 is 0. You can try that in your calculator. 2857. Okay, 0.2857. So this is how you can use the formula for conditional probability to solve problem like this. Before I move on to part B, do you have question on part A? Yes or no? Look like there is no question. So let's move on to part B. So in part B, similar question, if a bird is selected at random, find the probability that the bird is a male. Okay, probability that it's a male. And then given that, we write like that, given that it has blue eyes. Blue eyes. Now, if I want to write the formula for this, this is a conditional probability because we are given that. So it will be probability of first and second. So that is probability that it's male and blue-eyed divided by probability that it is a blue-eyed bird. So that's equal to, if we plug in the values, in the numerator, I'm looking for probability that the bird is a male and blue-eyed. Male and blue-eyed, I have 20 birds. A male bird with blue-eyed, I have 20 birds out of 100. So that is 20 over 100. Divided by, in the denominator, probability that it's blue-eyed bird. Blue-eyed bird, I have 30. You can see these 30 birds are blue-eyed bird out of 100. So the probability will be 30 out of 100. So again, 100 and 100 cancel, we get 20 over 30 or 0.6667. So this is how we can use the formula for conditional probability to find the probabilities. And remember here, in this example, we created this contingency table, okay? In most of the problem in your mastery exercise, the contingency table is already given, but you must be able to read the table properly. If the totals along the row and columns are not given in any problem, first you have to find those totals because they will also help you answer the question easily. Before I move on, is there any question on this example? Just say yes or no.
No.
Okay, good to know that you're getting it. So finally, the time for the last example from this unit. Okay, let's see what is going on in this example. Out of 46 selected group of students at a university, so 46 students are selected, okay? In that group of students, 24 are seniors, okay? 24 students are seniors, 28 are nursing. So now see, 24 are seniors, so that means they are the fourth year, I should say, freshman, sophomore, junior, and then senior. So these are the fourth year in the college. 28 are nursing. When I say 28 are nursing, they can be freshmen, they can be sophomore, they can be senior, or they can be junior. They can be junior or senior, okay? So they are from all over the place, freshmen through seniors. And 6 are neither. And the 6 students from that 46, 6 students, they are not seniors. So that means they may be freshman, sophomore, junior, and they are not in nursing. So they may be engineering or some other thing, okay? So that is the different demographic that is given in the problem from that selected 46 group of students. Total is 46. Now, if student is selected at random from the group of these 46 students, what is the probability that he or she is a senior? So let me write this. Probability that he or she is a senior. Let me write SR for senior. Senior, given that means we write like this slash, given that the student is nursing major. Nursing major, we write NU for nursing here. So you can see this is the conditional probability. Now let's try to use the formula and see if we can solve it easily. So this is the conditional probability. The formula for conditional probability will be probability of first and second, that is probability that the student is senior and also nursing major, divided by the probability of the second, that is probability that the student is a nursing major. Okay, interesting. Now, see, if I want to find this, if I want to plug in the values, the total is 46, no doubt on that. But here in the denominator, I have probability that somebody is nursing major. Yes, nursing 28. I have 28. So 28 out of 46. So I can do the denominator easily. But if you look at the numerator, senior and nursing. So how many of these 28 students are senior? We don't know. Okay, we don't know how many of these 28 students are senior, or how many of these 24 students are nursing major. We don't know. So we don't know anything common between these, because some of the senior students are nursing major, some of the nursing major are also senior. So we don't know what is there in common. So we have to find that common first in order to use this formula. So that is the tricky part here. So what I'm going to do is I'm going to represent this information using a Venn diagram. So let's do this. Senior, let's write senior SR, nursing NU, total students in that group, that is the sample space S. Okay, I'm trying to represent that. Oh, sorry about that. Let me share it again. Okay, let's see. Can you see my screen back again?
Yes.
Okay, good. So now see, seniors here, nursing here, the entire group of 46 students, that's my sample space. Now we don't know what is common because that's what we are looking for. How many students are senior and also nursing? This common part, we don't know what is that. So I'm going to consider that as X. Okay, I'm going to consider that as X. Now, if you look at seniors, everybody look at the screen. Seniors, we have 24 students. 24 seniors, out of 24, X is here. So this side we should have 24 minus X. Out of all seniors, X nursing measure, so the remaining will be 24 minus X. Similarly, total nursing students are 28. Out of 28, X are senior, so the remaining will be 28 minus X. And then we already know that 6 students are neither. That is, they are not senior, they are not nursing. So 6 students would be outside. So out of, you can see out of 46 students, 6 students are here. Okay, out of 46 students, 6 students are here. And the remaining students are right here. So if I add all these students, it will be 40 because 6 are already here. So the remaining students will be 40. So if I add this 24 minus X and then X and then 28 minus X, that will be 40. This equation will help you to find these students in the middle, the common students, senior and nursing. Before I move any further, are there any questions? Are we clear so far?
Yeah.
Okay, good, very good. So now let's solve this equation. See here, X and X cancel. X and X get canceled. 24 and 28, if you add those two, 24 and 28, how much is that? 52. Okay. Did you say 52?
Yes.
Good. 52. And then here is minus X equal to 40. So if I bring that 40 on the left hand side, that will be negative. And if I move the X over, that will be positive. So that means X equal to how much? 12, right? X equal to 12. So when you solve this equation, the basic algebra there, when you solve that equation, the value of X is 12. So that's what we are looking for. How many students are senior and also nursing, right? The common here, senior and also nursing was X. So that is 12. So we are going to plug that value here and we'll get the result quickly. So this is equal to probability of getting senior in nursing. Senior in nursing is 12. Probability that the student is senior in nursing is 12 out of 46. And then probability that they are nursing measure, we have 28 out of 46. So now you can see 46 and 46 cancels. It will be 12 over 28. And then 12 over 28, if you try to simplify that, 12 divided by 28, if you try to simplify that, it will be 0.4286. 0.4286. So that is the probability that the student is senior and also the nursing measure. So that is the end of the lecture for this, I should say, for this unit. Okay.